Hello everyone. Today we're going to do our 8th lab, and in this lab we're going to talk about something called LED CPU. Now, LED CPU is a simple CPU design which has only two instructions. These are output and jump. So these instructions are only 16 bits long and are structured like this. So here, as you can see, we have from 0 to 15, 16 bits. And for the instructions, we have different patterns. So for an output pattern, we have the pattern here, and then some non-zero value in this slot from 0 to 7th bit. And from 8th to 15th bit, we have a pattern that we want to display. For a jump instruction, we have 0 in from 0 to 7, so all of these bits are 0. And in 8th to 15th bits, we have an address to jump to. So since we make the distinction of these instructions in this delay slot here, we don't actually need a opcode. So if you'll remember, in a very simple CPU, we had opcodes, 3 bits and then an I bit, so a total of 4 bits for the opcode. But since we make the distinction of these instructions by the delay, it being either 0 or not 0, we do not need an opcode. So that's why this is actually the entirety of our instructions. So here you'll see a bit more details of what's going on here. So as I've said, if the delay is a 0, that means this is a jump instruction. And if delay is not equal to 0, it's equal to an output instruction. So the jump, I think we're all familiar with the jump at this point. So if I encounter a jump instruction, I'm just going to change my program counter. For an output instruction, what you're going to do is you're going to output the pattern given in these bits from 15th to 8th bits in your LEDs of the FPGA. And you're going to do this for this delay times. So this delay quantity is going to tell you how long you're going to display this pattern. And after this delay is done, you're going to move on to your next instruction, meaning you're going to increment your program counter. And our jump instruction in this case doesn't have any conditionals, so you don't need to do any checks. You jump straight away. It's like BZJI. Okay, let's keep going. So here we have an example. So say we wanted to make a rotating dot with this LED CPU. So you'll remember the rotating dot is the first lab we did with virtual FPGA. So if you'll remember, what happened was the LEDs were going on from left to right. So this table actually gives you that pattern. So we started with this turned on and everything turned off, and then this bit shifted right at every increment. So it's 0, 1, 0, 0, 0, 0 now, and then one more to the right, one more to the right, one more to the right, and all the way until down here, where after this it would loop back to stage 0. So let's say we want to do this in our LED CPU. So the way to do that would be something like this. So here, these are our instructions, and let's actually see what's happening here. So first of all, in my first instruction, let's check if this is a output pattern, an output instruction or a jump instruction. And for that, we're going to check these bits. So let's look at the least significant 8 bits. We got this. So this is a non-zero value. It is not equal to 0. That means this is going to be an output instruction. And our output is going to be this. So the next instruction, again, it's a non-zero delay. So it's going to be an output instruction. And my new pattern is this. And the next one, same, and it keeps going like this. And you'll see that this pattern actually is the same as this one. So this way we're going to display the rotating LEDs. But one last thing to remark is this 8th instruction right here. So as you can see, in this instruction, there is no delay. So delay is 0. That means we're going to jump. And where are we going to jump? Into this address, which is 0. And this 0 address is here. So address 0. So we're going to jump back to the beginning. This way, our code is actually going to loop. So the rotating dot will go on forever. So that was a simple introduction to the LED CPU. We discussed the instructions, we discussed the word patterns, and we showed you an example of a working program. So before we actually get to your assignments, we have a quick question that we want you to answer. And I'm not going to go through all of this, but basically we want you to find the delay value that corresponds to this guy here. And one thing to note about this is you're going to look at your Verilog files and you're going to try to understand what this delay value actually means. Alright, so let's take a look at our assignment then. So your first assignment is the LED CPU with ROM. So you actually have, well, 3 assignments, but basically you need to implement 2 different designs. The first one is LED CPU with ROM, and the second one is LED CPU with RAM. And you can actually see the details of this in the PDF that we gave you here. So let's take a look at LED CPU with ROM. So we already talked about this. So this part is describing your instructions, and your design is going to look like this. So you're going to have a reset, a clock, and an out pattern. So reset and clock are self-explanatory at this point, and your out pattern is your LEDs. So this should be 8 bits, not 7 bits. I'll fix this later. So at the core of the design, we have the ROM. So ROM stands for read-only memory, meaning we can only read from it, we can't write to it. And let's actually take a look at its structure. So it has the usual address style. So from starting from 0 goes up to 2 to the 8 minus 1, meaning 258. And this of course means the address is going to be 8 bits, because the maximum number I can write with 8 bits is actually 2 to the 8 minus 1. And we also have the data out. So if I wanted to read from this ROM, what I would do is I would input an address, and in the next cycle I'm going to get the value of that address in my data out. So this is how the ROM works. So this is where your program is going to persist. So, and since it's only ROM, you're going to write your program before you start running it, because we cannot alter the ROM after we start the program. And here you can also see the design behaviors that we've talked about, but let's take a quick look. So as we've said, the ROM has 256 entries, and each of them are 16 bits long, and the second 8 bits, so the first 8 bits are the data or address, so the output pattern or address for jump, and the second 8 bits are the delay time. So your design is going to start from the 0th address, and it's going to keep incrementing the address, so the program counter. And if you encounter a jump instruction where the delay is equal to 0, you're going to change your address to the new one given in the argument for the jump instruction. For an output command, you're going to display the output and wait for the delay time. Alright, so with that said, that's the first one. So let's actually take a look at the files that you're going to be working with. So for LED CPU with ROM, you have these files here: your top wrapper, your LED CPU with ROM, LED CPU core, ROM, and delay. So let's start from the top. So in your top wrapper, it's your typical top wrapper. So we have our clock bind to this, so reset, we have it set to button 0, and the output pattern of LED CPU with ROM is bound to our LEDs. So that's pretty much it for top wrapper. Then we have your LED CPU with ROM file. Here we have clock, reset, and out pattern. And in here, you're going to initialize both the core and the ROM. So the ROM we've talked about, you have a address read and a data write. Address read and data read. And then you have your core. And here, before we actually take a look at these, I want to make a remark on these values here. So you have two parameters here. Your first parameter, your frequency, and your second parameter, the delay. And sorry, this should actually be 16. There we go. Okay. So the frequency defined here is 50 million, and this stands for our frequency of 50 megahertz. So usually when we're working with working in our labs, we give you our FPGAs, and those FPGAs work in 50 megahertz. So this is what that is defining here. And then this frequency delay parameter is something that you use in the program to tell it how much you want it to wait. And as you can see right now, this is set to 1. But normally, if you were working with an FPGA, you would set it to this value. But since we're not working with an FPGA, instead we're working with the virtual FPGA, we're going to lower this value because virtual FPGA is much slower than an actual FPGA. But one important thing is that, so if you go back to your PDF here, you'll remember a question. So this question, for this question, you're going to use the commented out value, this value here. Don't use the 1 here, use this to answer that question. But with that being said, I think that covers this module. So next up, let's take a look at our ROM. So the ROM file is here. So it's pretty basic. So it's actually got the rotating dot that we discussed. So we have this pattern, and as you can see, we have the delay value set to 128. But this is not 128 seconds, it's not 128 milliseconds, but it's something else, and that's actually something you need to figure out. So with that being said, this is the ROM, and so all you need to do is enter an address and it will return you the data immediately. But next up we have the SLED CPU core, so let's take a look at that as well. So this is the actual file that you're going to write to. So here, let's look at our ports first. So we have our clock, reset, address read, data read, and output pattern. So these address read and data read are actually connected to the ROM. So if we take a look at this, so this address read port, it has this wire here, address read wire, and that is connected to our ROM. And similarly, in this port, we have the data read wire, which is connected to the data read of the ROM. And then additionally, we have the output pattern, which is the pattern that you're going to display with your LEDs. Alright, so other than that, we have our always at posage statement here for your flops and our always at star. So here we already gave you the default statements, the reset statements, and what you need to do is write your design here. So you're going to implement the design where you increment the address, and based on the address you either do a jump operation or you do a output display operation. And also here, one thing to remark is we have a module instantiation called delay, and all this does is actually it counts up to the value that you enter for here, so the frequency delay. So it might say this value here, but this is going to get overwritten from here. So the topmost initialization value for this parameter is the most significant. So this value is going to be 1, and you actually use it here to initialize. So it's going to get overwritten here. So it's going to be 1 for our virtual FPGA. And this delay value will count up to this value and output 1 when the counting is done. So if this was for our actual FPGA but not for virtual FPGA, it would count up to this value here, and then and then it would output 1 for 1 clock cycle. And that is actually how you produce the delay for this program. So you're going to use this value to, sorry, this module to do your delays for displaying. So that's about it. So when writing this, you can have, I think we gave you everything. You don't really need to define much else, but if you need to, of course, you can always define more registers. And so all you need to do is complete this part. And once you complete it, so that will be the end of this task. Here, so you're going to complete part 1. And for part 2, well, before you go to part 2, actually, what you need to do is synthesize your design and run this program on virtual FPGA. So let's actually take a look at how this program works in virtual FPGA. So here I have my virtual FPGA and I already programmed it. So all of these files are in here. And so, as I've said, the virtual FPGA is much slower than an actual FPGA. So for this lab, what I recommend is you go to the Options, Settings, and here you'll see a few values. And these values are actually used to determine the speed of your virtual FPGA. And since this is a relatively complicated design, if we don't lower these values, it is going to be a bit slow. So for simulation delay, what I recommend is 0, iteration per clock cycle 4. So these are the values that works for my configuration. So if it does not work with you, maybe try something greater than 4. But if you enter something too big, your design is going to run a bit slow. But anyway, once you enter these values, just press OK. And let's actually start. Sorry, did I not press start? There we go. So, okay, we have our program running right now. So it might get stuck here, so press reset, and there we go. So, as we'd expected, inside our ROM, we had the rotating dot. So that is exactly what our program is doing right now. It's doing a rotating dot. Okay, so with that, we've actually now completed part 1. So let's take a look at part 2. So for part 2, we want you to actually modify your ROM file. And what we want you to do is we want you to write a ROM file where the delay for rotation is going to be 1/4 of a second, and instead of doing that's it. So you're going to have a right to left rotation again, but for 1/4 of a second. Now again, we have an issue here. So we want you to do this for an actual FPGA with the value that we gave you here. So again, calculate the delay based on this and modify this ROM file according to it. So based on this value, find the delay such that the transitions will only last quarter of a second. And then if you run the program with that, well, you might not see exactly quarter of a second, so it actually depends on the speed of your computer. But you will see that the program is actually running a bit faster. Alright, so with that, the second part is also complete, and let's take a look at part 3. So in part 3, we're going to do LED CPU with RAM this time. So in LED CPU with RAM, you're actually going to use the files that you've written in part 1. So you're actually going to use the ledcpu.core that you used in part 1. And what you're going to alter in this case is a new file called proglogic. So what we want you to do with this is actually, well, let me actually show it to you from here. So we will also provide you with this PDF, and this will detail the exact details of LED CPU with RAM. So this time we're going to read our instructions from a RAM instead of a ROM. Now what this signifies is that we can actually alter the contents of a RAM while the program is running, right? So in ROM, we can only read from the ROM, but in RAM, we can actually read and write to the RAM. Otherwise, so it's going to have the jump and the output operations once again. And here is a basic structure of your modules here. So first of all, you have the LED CPU with RAM. This is your top module. Then LED CPU core. So this is the file that you wrote in the previous part, which you don't need to modify. And then you have 2 additional files here, 2 additional modules. So let's actually talk about this first. So this is a RAM module where you will read and write your instructions, and you have your prog logic, so your program logic basically, where you're going to well, interact with your I/O, your buttons and switches. And how exactly you're going to do this, so I'll come back to this later, is defined in this slide. So this time, the program will start with a empty memory. So it will start with all zeros. And all zeros in this case, of course, means jump to 0. So it will do nothing but just stay at address 0. What we want you to do is fill the contents of this memory using the switches and buttons. And how we're going to do this is, since the RAM has 16 bits, just like the ROM, we're going to have to use the switches 2 times. And you're going to use a similar approach to the one that you used in your previous lab. You know, you remember we did the calculator, where we needed to enter one number, one operator, and then the second number. And how we did that was enter through switches and then press an enter button. So similarly, this time we're going to divide the instruction into 2. So if we actually go back to our PDF, so this was our word pattern. So this is how our words were structured. What you're going to do is first enter this part of your instruction, press enter, and then enter this part of your instruction, and then press enter once again. So using this, you're going to fill your memory, your RAM with this. And you're going to do this sequentially, meaning that first you're going to write to address 0, then you're going to write to address 1, address 2, address 3, and so on and so forth. Additionally, we have details regarding how to write to the memory, and I'll discuss that in a minute. Other than that, so that's it. This part describes you exactly what I just said. So you're going to use the switches and the buttons to enter your data. And okay, so that's about it in this part. So let's actually take a look at our memory to see how we're writing to it. And let's actually first let's take a look at the module that you're actually going to write. So in this module, you have your switches. These switches are the switches on your FPGA, your enter button. So the switches are 8 bits, the enter is 1 bit, your clock, reset, and then we have data write, address write, and write enable. So you said that we can actually both read and write to the RAM, but this part of the program only needs to write to it, right? Because the reading is done by the LED CPU core that you wrote before. The program logic will only write to the RAM. So that's why we only have data write, address write, and write enable. And the way to use these are as follows. So let's say I want to write the value 5 to address 0. What I'm going to do is I'm going to write 0 to address write for 0th address. I'm going to write 5 into my data write here, and then I'm going to write 1 to my write enable. So the write enable signifies that I want to do a write operation right now. So if you don't do write enable equals 1, it doesn't do anything. So again, if I want to write 5 to address 0, address is equal to 0, data is equal to 5, and write enable is equal to 1. That's all I need to do. And that actually covers the program logic. And we can actually take a look at the memory as well. So it's going to have the corresponding ports to the ones that we discussed. So the data write, address write, write enable. And additionally, it's going to have data read and address read from the LED CPU core. So these are the same as the ROM. So I'm not actually going to discuss them. They're just connected to your old module, LED CPU core. Okay, so this is actually a very nice view of the program, which we will also take a look at from the Verilog files. But we've already gave you this part. So, well, this is from your previous assignments. You're going to use this. We gave you this. All you need to do is write the inside of this module. So with that being said, let's actually take a look at our Verilog modules and see how this works. So here I have my files, and from top to bottom, first of all, I have my top wrapper for virtual FPGA. Here you'll see it has clock, reset, switch, enter, and output pattern, initializing my LED CPU with the RAM module. So it's the same as usual. So we have two things to remark here. The reset button is set to button 0, and the enter button is set to button 1. And next up, we have our LED CPU with RAM. So this is going to be similar to your LED CPU with ROM, but we're actually initializing a few different modules here. Sorry, this should be, there we go. So as we discussed, we have clock, reset, switch, enter, and output pattern. And again, you'll see we have a parameter called frequency, and normally it would be this value here, but because we're working with virtual FPGA, we set it to 1. And then we have the modules that discussed before. So actually you can actually construct this diagram here just by looking at this here. So we have all the ports and the modules defined here. You can read it from here and construct this diagram right here. Well, as we discussed, the LED CPU core is the module that you write in your previous assignment. In this case, this part is empty, but since you're going to copy it from your previous assignments, you don't need to change anything else. And then we have our memory. So this memory, as I've said, can read and write. And it only consists of a single always at POSH clock block. And additionally, it has this part right here. This is not for synthesis, this is just for simulation and virtual FPGA. All it does is it initializes the memory with zeros. So this is the init file that's in here, so init.v. All it does is put zeros in all of the array elements. So that's it. And next, so delay, we've talked about delay in the previous assignments. And finally, we have your program logic. So for program logic, we're actually not giving you anything. We want you to write that from the beginning. So we already gave you the port assignments because, look, they're defined in here. Clock, reset, switch, enter, address, data. You can define the ports looking at here, and you can actually find out the widths of these as well. So for example, switch, how big is the switch going to be? Let's look at this. There we go. So the switch is going to be 8 bits wide, and enter is going to be a single bit. So using this here, you can actually initialize, well, not initialize, write the ports of program logic. And this program logic, as I've said, is going to read the, well, it's going to read your switches and your buttons, and it's going to enter these values into the RAM. That's all it's going to do. So it's going to write into, starting from address 0, and once you're done actually writing to that address, it's going to write to address 1, then address 2, and address 3, so on and so forth. So that's all there is going to be inside this program here. So that actually covers all of the Verilog modules as well. So all that we have right now is the virtual FPGA. So here I already have my virtual FPGA. So as you can see, I have all of my files here, and I'm actually going to do the same thing I did before. So let's set this simulation delay to 0, and iteration per cycle, let's set this to 4, and let's start. Okay, so our program is running right now. So at the start of the program, you're probably going to get a random pattern right here. So get rid of that by pressing the reset button. And let's actually write a program inside our RAM. And let's go with a rotating dot as we did before. So the rotating dot begins with this. So I press enter. And then let's enter a smaller delay. Let's say go with 4. And immediately I'm going to see my LED appear. So why? Because inside my memory I only have the first instruct is the 0th address set as an output pattern with this, and the next one is actually 0 pattern, which is go to address 0. But let's try something else. So the next one is going to be like this, and let's go with the same delay. There we go. So now it's just rotating between these two. So let's keep going. Now it's rotating with these threes. So let's just keep going. This, and then this, and so on and so forth. So you're going to keep doing this to create some program like this. And one thing I want to note is that since the virtual FPGA is running a bit slow, sometimes the buttons don't work properly. So what I mean by that is if you do a very quick click, sometimes the program runs a bit too slow and has some problem catching it. So when you're setting something, so let's say I'm doing the next pattern, when you're pressing the enter button, just press and hold for like 1 second. That'll ensure that the virtual FPGA can actually catch your input. But yeah, so that's it. So this is how your third assignment is going to work. And with that, I think we're actually done. So let's go back to our PDF. So you've modified the prog logic file here. Okay, yeah, that's it. And for submission, you're going to send your prog logic, your LED CPU core. Also, I will add it here. Also send your modified ROM file that you did in part 2. And then send the answer of this question here. So for this question, don't just send an answer. Show us how you found your value. So show us your work and handwrite that. So write that on a paper, take a photo, and put that photo in here. And additionally, we want your synthesis screenshots for part 1 and part 3, and that's it. So as usual for synthesis screenshots, show us your warnings, make sure you have your no errors, make sure you do the synthesis. So once you do that, you're actually done. So thank you for listening,